So I'd like now to derive some equations to describe a continuous stirred tank reactor, or CSTR as it's frequently referred to. And as the name suggests, CSTR is often a mechanically agitated or stirred vessel. Often it's jacketed to provide heat transfer, so schematically it looks a little bit like that, and it has a feed which we're going to say has a flow rate of Q meters cubed per second, and that has a feed component A, which is a starting material whose concentration in the feed is Ca0, and that's expressed in moles per cubic meter. And the total flow rate of our component, molar flow rate, we're going to say is Fa0, and that is equal to Q multiplied by Ca0, and F then would be molar flow rate in moles per second. Okay, we're going to say that our reactor has a volume of V, cubic meters, and then there's an output stream. So usually the output stream is arranged to give a constant volume inside the reactor, which we'll come on to in a moment, but that we're going to say also has a flow rate of Q meters per second. It has an outlet concentration of our starting material Ca moles per cubic meter, and again we can have a term for the molar flow rate of component A of Fa moles per second, and Fa is related to Ca and Q in exactly the same way as it was for the input stream. So that's the output stream, that's the input stream. Let's just talk a little bit about assumptions, because these are quite important and just help to make the derivation a little bit simpler. So first of all, we're going to assume that the tank is well mixed. So that means that the composition at any point in the tank is the same. And the consequence of that is that we're withdrawing the output stream. It may be from the bottom of the tank, maybe from the side, on a side arm, but wherever it comes from in the tank, the composition of the output stream will be the same as the tank contents. So this concentration Ca in the output is representative of the composition of the contents of the tank, and that's because the tank is well mixed. We're also going to assume that we're at steady state. So this is a continuous process. Flow in and flow out are not varying, and the composition of the tank is not varying, so there are no changes in composition with time. And it's already implied in what I've written, but we're going to assume that we have constant density, so that the volume in is the volumetric rate in is the same as the volumetric rate out, and that's if the density of this stream is equal to the density of that stream, and because it's well mixed, we know that that's the density of the contents of the vessel as well. Okay. So to derive the equations, we do a material balance again, and we use the usual material balance equation, which is input minus output plus generation equals accumulation. So in other words, the input, what goes in minus what comes out, plus any generation or consumption of material equals the accumulation or the build-up of material in the system. Now we've said that we're at steady state and that there's no change in composition with time, so that means that the accumulation actually equals 0. So that tells us that we can sum these three terms and the net result of that should be 0. So input, if we do a component material balance on our input material A, so the input is FA0, the output is FA, and the generation is the reaction term. So we can define a reaction term RA in moles cubic meter per second, and that's the rate at which A is reacting. And because A is being consumed, then actually RA would have a negative value. So that's the reaction rate. So these are in moles per second, so we need to multiply our reaction rate by the volume. So the reaction rate multiplied by the volume gives us the rate of generation. In this case it's the rate of consumption, because RA will be a negative number of hours to material A. If you sum those three terms together, it's at steady state, so that equals 0. And then you can take this term over to the right hand side and just rewrite that then, and divide by V, and we get minus RA, because we've taken it over to this side, so it's become minus, equal to FA0 minus FA divided by the volume. And we can use this relationship here to state that in a slightly different way. So we can also get that RA minus RA is equal to Q over V multiplied by CA0 minus CA. So I've just rewritten the molar flow F as the volumetric flow multiplied by the concentration. Taking the Q out, so we've got Q over V multiplied by CA0 minus CA, and that's the first form of the equation to describe a CSTR.